Okay, welcome everyone to today's CDAC webinar. It's a real pleasure to introduce an old friend, Igor Babaev. Igor is a leading theorist in the field of new quantum states of matter, including new superfluid and superconducting states, and some of this arises under extreme conditions. So we're extremely interested in having him give a talk in this series. Igor received his PhD in theoretical physics from Uppsala University. In 2006, he joined the faculty at the KTH Royal Institute of Technology in Stockholm. And in 2007 to 2013, he was also a professor at UMass. He's currently a full professor at the Royal Institute of Technology. Igor has won a number of awards for his pioneering work in this field, including the Gustafson Prize, APS Fellowship, and the Erlander Prize. I first became aware of Igor's work with a series of papers he wrote with Neil Ashcroft in the early to mid 2000s, work that's inspired a lot of thinking, at least, not experimentation, looking for new states of matter and dense hydrogen. And we're delighted that he's agreed to review some of that early work as well as give us an update on some of his newer work in the field. So over to you.
Good, thanks, Russ. Thank you very much for invitation. I always enjoyed my interaction with high pressure community, and I really think it is like I really respect the community and hope to think about these problems again. And I like put on the front slide some of my snapshot of my group a few years ago, but just wanted to say there were much more people contributed to this research, and I don't have photos of all of them. I should at some point have a large set of photographs because of the very many people who contribute fraction of early works on this topic I will be talking about were actually done thinking about metallic hydrogen type systems. So, but let me just start with like basic known things. So we know like superconductivity is a pairing of electrons, right? And just let me list like general known milestone, like what do we know about occur about pairing of fermions, electrons in particular, and what are the key consequences. So, okay, the like in superconductivity, like there is typically a single critical point where a system becomes superconducting, and electrons pair at this transition or before can form preformed Cooper pairs. And then, like, what are the key concepts? The concept of pairing of electron, I think to the best of my knowledge, the earliest discussion of that, like occurring in principle, was by Feynman. Without theory, he could not come up with ideas how they would pair, but he says that if they would pair, he could explain superconductivity. And then phenomenological theory, London model to me is the most impressive work in superconductivity. And like later it was understood as a consequence of pairing. And then typology of superconductors, type 1, type 2, a concept of quantum worlds by Onzager and Feynman also, and London, and then applied for typology of superconductors by Abrikosov and finding vortex slates. And then it was generalized to many other things. So, and introduced many other concepts. The observation was a big breakthrough, like superconducting energy gap, and then pairing of electrons. BCS theory, basically, BCS theory was generalized to pairing of quarks, Nambu, Ion Lazinio, and that's Nobel Prize by itself, and Then it was generalized also to pairing of atoms. We know helium-3. It was generalized to pairing of nucleons in large nuclei and neutron stars. And then also it was BCS theory was also version of the BCS theory was generalized to pairing of quarks in dense quarks matter, like for example in the interior of a neutron star. And these are a pairing of fermions was extremely fruitful topic over more than a century. And then the question is like, if one looks at the kind of paradigm of BCS theory, then only pairing can occur. So if one just if one raises the question, that's the kind of question I was wondering when I was PhD student, like back in 2002, like when reading just first books, like could electrons form quadruplets, and could there be the case that electrons condense in groups of four rather than in pairs. So like, of course, like in BCS theory, it is not possible. And then, so it's not like entropic, energetically or entropically winning, would not win over pairing, at least in standard BCS theory. It's not even possible to, within the whole like framework to treat it. One cannot introduce this counterpart of this four fermion mean field. And then actually there was a series of papers like in early 2000 which proposed where we proposed a mechanism how one can achieve actually condensate involving four electrons, or actually it was a large part of works like this one was actually done in context of metallic hydrogen, and then the proposal there was if hydrogen would be in a metallic state, and if one would have pairing instability for both electrons and protons, or if you would have liquid metallic deuterium, then there is a mechanism how one can form a higher order composite superstate, a new type of superstate with a like with a higher consisting of a higher kind of composite objects. And there was like very close proposal at around the same time by Kukulov, Svistunov, and Prokofiev for bosons, mechanism for boson pairing and bosonic counterflow condensate, and they exploited a different physical situation, proximity to modern insulator and multi-component systems. Later it was generalized to other systems. So, so let me just outline like what is like the beyond mean field picture of superfluid or superconducting phase transition. So if one has, let's say, superfluid, one breaks U1 symmetry associated with the existence of the phase variable in a complex field, in a classical complex fields, which described by superfluid, and then it is disordered by, this phase can be disordered by vortex proliferations, by proliferation of a single quantum vortex, and in two dimensions, this is a Kosterlitz-Taulis transition, vortex anti-vortex pairs and binding that drives phase transition from algebraic long-range order to normal state. In three dimensions, that could be in principle described by like phase disorder installation of U1 symmetry. It could be mapped on the problem of proliferation of directed loops, like under certain conditions, one can think about proliferation of the vortex loops. And so all this, like not always, but in many cases for restoration of symmetry of U1 symmetry and disappearance of superconducting superfluid state is driven by quantum forces. And so now, what do we know about all of this, all the paradigm of, let's say, Kosterlitz-Taulis transition? What is important there is that in the superfluid velocity is quantized, so that there is like minimal vortex that one cannot have like in the classical fluid arbitrary vortex. The vortex actually comes with quantized vorticity, and then the phase transition is driven by most simple objects which carry just one, yeah, with the minimal possible circulation. That's 2 pi phase binding basically in this phase theta. And all the other type of forces are irrelevant for this transition. And the same is for like if one wish to map phase transition in 3 dimensions to vortex loops, that is the same situation that only the most, the basic, the cheapest topological defects proliferate in derive phase transition. Now, then let us consider the simplest model, the simplest generalization of the superconducting state. So, and for that, one of the simple system that in that respect that we considered is like simple in the sense simple by symmetry is metallic hydrogen type of systems. Like suppose one was able to form like if one starts with a conjecture that one is able to form pairs of electrons and pairs of protons simultaneously, then because of one cannot convert electron to a proton, they will be independently conserved condensates. There were two conservation laws, and there will be necessarily two fields. And like if one writes the simplest, basically hydromagnetostatic problem of a two-component superconducting state, that's not just a metallic hydrogen type of system. Like if one goes deep enough in the interior of a neutron star, then sigma minus gyperons, for example, become quite stable. And in principle, they also can have Cooper pair instability, and they could be like also condensate of protons and condensate of sigma minus gyperons, and they would be two complex fields as an example. So of course, like if one would talk about electrons and protons, there should be different sign of coupling to gauge field, but that the precise sign is not important. One can map a mixture of two equally charged condensate onto a mixture of oppositely charged condensate if one's careful with keeping track. So let me just now focus on just two-component superconductor, basic London models, two-component superconductors, two fields coupled to the same vector potential. And then one may ask a question, what happens with the phase transition in the system? And then like if one tries to think about it in terms of this in spirit of Kosterlitz-Taulis and spirit on Zagier and Feynman, one needs to identify what is the simplest type of topological defects. And then actually one first big difference can be observed from compared to ordinary system. And that can be observed also at the level of this the basic simple model. So first of all, let us take a London model, but now for two components. One can separate variables. One can just rewrite this model and extract gradients of the phase sum and the gradient of the phase difference. And here, when one has a gradient of the phase difference, there is no coupling of the vector potential any longer because one takes the gradient of the phase difference theta 1 and theta 2, the coupling to vector potential will be cancelled. And this term will look like if it is a gradient term for a superfluid. And if one collects all the other terms, there would be some gradient of the phase sum coupled to vector potential, and then there will be magnetic field energy density. This is just a rewriting. But now, if one starts thinking about elementary vortices, one can immediately see that there's a dramatically different situation compared to ordinary examples which I listed earlier. Here, if one would start winding phase one, here it is not the winding in the phase one can in this term cannot be asymptotically compensated by vector potential. There is no vector potential here. So this thing in the brackets will go as 1 over r, 1 over the distance from the center of the vortex core, and it will have logarithmically divergent contribution if one puts in a vortex in the phase one. So, and if one has a composite vortex where both phases y by 2 pi, this term is cancelled, it is 0. And as we'll see below, that means that elementary vortex in this system has logarithmically divergent energy, while bound state of two vortices has a finite energy. It has very important consequences for phase diagram of the system. So let us look at the now at elementary vortex, means vortex where only one phase winds by 2 pi. And then one can write a most standard equation for supercurrent, just standard London-Ginsburg-Landau, in that case, equation for supercurrent. And then one calculates the supercurrent of a vortex with phase winding only in component 1. And then there is only one phase gradient in such case, and so only one of these terms has a phase binding. We retain only, let's say, component 1. And then one does a vortex magnetic flux argument. One expresses vector potential through everything else and integrates it over a closed path around the vortex. And then one can see that such a vortex could carries only a fraction of the magnetic flux quantum. This vortex is no longer does no longer carry a magnetic flux which is a function of fundamental constants only, but it carries can carry arbitrary fraction of the magnetic flux quantum, which is just given by the ratio of this basically of these fields. And so one can find detail in this old paper, like now it is almost a quarter of a century ago. And then the main thing is, however, like the important thing is like one can fractionalize flux quantum of such system. And the reason is why flux quantization is no longer universal in the system is basically a frustration. So another, like if one looks back at this type of basic, like a London model, and here if one winds phase, like what is the origin of the usual flux quantization argument? If one would have only field psi, one winds phase of this psi of this field by 2 pi, one gets a gradient of this phase, and then one can asymptotically compensate this gradient away from the vortex core by enclosing one flux quantum and getting finite energy solution. But now, if one has two component and only one phase gradient and tries to compensate this phase gradient by enclosing one flux quantum and means vector potential, here in this other term, vector potential will also appear and will make this term logarithmically divergent. So this is basically a frustration that where a system minimizes energy by fractionalizing magnetic flux quantum. And then this is what was in our Nature paper. We looked at what is the consequence basically for the phase transition in the system. And then if, again, like starting under the assumption that we have some kind of system, be it like metallic hydrogen, be it like condensate somewhere in a neutron star, then if one exposes it to magnetic field, it's one of the example, and then the only finite energy vortices it could form in external field will be the vortices which have composite nature, that will have winding in both condensates. And if one would form winding only one condensate, let's say electronic, then such a vortex would carry logarithmically divergent energy and carry only a fraction of the flux quantum, and correspondingly would wind phase, like if you have existing protonic condensate, you wind phase zero, and that would also carry a fraction of the flux quantum, and also will have logarithmically divergent energy, but they will attract each other, like if they interact with Coulomb force, two-dimensional Coulomb force, and that so basically they tend to form these composite objects. And if you consider next the fluctuations in the system, this was our series of works from like starting from 2002 to 2005, considering phase transitions and such multi-component superconductors. And like an external field, basically there are several phases. This is the schematic phase diagram which was in this Nature paper, and like a trivial phase transition is let's say form a vortex lattice, and then you apply consider system with a finite temperature, and in principle like one of the processes that could happen, you can melt, let's say, protonic sublattice. You can tear smaller fractions away of higher fractions and melt it, and then basically there would be a lattice of only forces carrying only larger fraction of the flux quantum, and then a liquid of vortices carrying smaller fraction. And in that case, you disorder one of the condensate, but as the condensate keeps, it become still ordered. Or there could be interesting, and it's more natural, phase transition, where one melts this vortex lattice without tearing two fractions of the flux quantum away from each other. And in that case, you still retain broken symmetry. And like if one denotes phases by arrows, so that state, which we call metallic superfluid, is a state when there is order in the phase difference between components, but each of these component individually is not ordered. So this was like electronic vortex actually carries heavier, larger fraction, and this protonic vortex carries smaller fraction. So that was the proposal. And then the first thing that was done, it was actually observed in classical Monte Carlo simulation. This is just a simulation of the system at, so let's see. Yeah, the system at finite temperature. So this is like one can see at low temperatures, there is just composite vortex lattice. And if one hits the system, and then one scenarios that could happen, you tear protonic vortices away from electronic vortices. And in that case, this is just becoming first electronic superconductor before one hits further and one goes to completely normal state. But there is like in a higher or lower fields, there is opposite scenario when one first melts vortex slates without frictionalizing vortices. And in that case, system retains order in relative degrees of freedom. And like if one writes it in terms of the order parameter, so there are like four possible phases. One of the possible phase is where all order parameters, each size order parameter of fermion pairs, electron pairs, or Cooper pairs, and then one case is that you have two non-zero order parameters. In other case, you have zero, both order parameters is zero, and the most interesting case is the one where individually order parameters are zero, but the product is non-zero. So here it like is actually, yeah, it should be this for if one talks about like hydrogen type of systems, non-zero order parameter is actually a pair of electrons and pair of protons. So essentially, like physically, what that means. So this is a snapshot from a simulation or from Monte Carlo simulation of this vortex slates. So what is the glue basically for this type of quadruplets? That mechanism is you form very peculiar type of vortex liquid, which serves essentially as a glue. So if you have like vortex tangle with particular properties, so if you try to send a pair of electrons through this vortex tangle, it will be agitated and it will dissipate energy. If you send pairs of protons through this vortex tangle, it will also agitate it and dissipate energy. But actually, if you send two pairs or four fermions through these vortex tangles, it will be dissipationless flow. So that is basically the mechanism for fermion condensate. And so we also considered electronic systems, and I will maybe accelerate a little bit, skip few other cases, but we'll show like some work from 2010, three-dimensional work, actually some slightly more general models. You could have four phases, and this is that also applies to the like electronic system. One could have as a charge for E superconductor. This is just a counterpart of this metallic superfluid. Is the basically the state where the like if one writes it in terms of creation and annihilation operators, if one has electronic systems, the order parameter for the charge-free superconductor will have this form, and then this is the phase 5 on this phase diagram, and then there's like another control parameter which is dissipationless drag, so called, like maybe I will save a little bit time to talk about this more general phase diagrams. And for us, the most interesting for electron order was the one occurring in this corner of the phase diagram. It is where uh, one has a counterflow condensate. So whereas the order is in like in terms of the original, if one has like now two component superconductor which are equally charged, and then one has, let's say, two complex fields, and then when the order is in a product let's say you have two superconducting gaps, and then if the order is in product of gap 1 and conjugate gap 2, that or equivalently when we have order only in the relative phases of these gap fields, which means that you allow only counterflow of pairs of electrons, but not coflows, but no dissipationless coflows. And that was a state which I find like particularly interesting. And and essentially, these were the type of models which were considered like around 2002 to 2010. And then a little bit later, I could now switch gear a little bit. Oh yes, maybe one more comment, like one more remark, like from the theory of the phase, just phase, like if one looks at the phase transition, it's very interesting if one generalizes it to higher mixtures. Then there are also in principle two there are various type of fractional vortices, and then the one starts looking at, let's say, counterparts of Kostelis-Tauris transition or counterparts of vortex loop proliferation in 3 dimensions. That problems map onto problem of a screening of a color plasma, and plasma where there are several colors of electric charge, which is mapped onto colored charges, and it's interesting to consider screening. There are also counterparts of these problems that we're working on the quantum Hall system. It's a very actually three component case. If one has like a mixture of metallic hydrogen and deuterium, and you start now considering this single flux quant to start like fractionalizing in several species. This is like ionization of a color plasma, which is a really interesting problem. And it's like how this fractionalization occurs in 3 dimensions. You can have like several colors for electric charges. Again, I will skip most of these things. It also these transitions can be generalized to higher symmetries. So such phases also were found for SU2 and SUN models, and that's also a very rich and interesting topic. And finally, it was like a separate class of system I could just mention from just how rich this problem is. We termed it Baromean symmetry, which is just a type of a counterflow. You have an n-component system where you can the only kind of dissipationless flow where you can counterpropagate with like a boson or a pair from a different component without forming, like you can constantly exchange counterpropagating partner, and that leads to actually new type of hydrodynamics and a new type of, you can even talk about new type of gauge invariance. This is like very, I haven't updated references, but there are like recent very interesting developments also by Kuklov, by Leo Rydzikowski, and it's like also very, very rich problem, which actually like started maybe first considerations of this kind started in a connection of like various mixture of hydrogen isotopes. So, and now, so this, like I will tell switch gear a little bit and tell like our recent activities of where a partial counterpart of this state was observed in real electronic system. So one difference which arises if one considers electronic mixture is that normally one would have intercomponent Josephson coupling. So, like if one has, let's say, multi-band superconductors, then pairs in different bands are no longer independently conserved. And then, like if one looks at the London type of models, one needs to include like Josephson type of terms. But the mechanism which I outlined, which we were proposing since like early 2000s, in 2002, to form high order condensate, it relied on uh, two, uh, two ingredients. So for this mechanism, two conditions should be met. One of them was that system should break more than one symmetry, and system should have strong fluctuations. So, and if one has like a mixture of hydrogen atoms, one necessarily, by conservation laws, like one has like multiple types of Cooper pair instabilities, one necessarily breaks multiple symmetries. In electronic systems, uh, it will not come from basic multiband physics, but under certain conditions, it can even multiband system can break multiple symmetries, and this is a so-called S plus S superconductor. So one introduces the so here phi ij is the phase difference. So I switched a little bit notation. So phi ij is the phase difference between phase of this component of phase of psi I, phase of psi g. And if the prefactor, the sign of the Josephson term, such that system wants to have pi phase difference between components, and there are three components, there is another frustration, and then there is twofold degenerate phase locking between components. This is called S plus IS state. And basically, the additional degeneracy, despite of existence of this phase locking terms, this additional degeneracy, one can have like this configuration of the phases or that one, and one cannot rotate this configuration of phases to that one by U1 transformation. Instead, you go by time, so you can go from this to that configuration by applying time reversal operation or complex conjugation. So this defines as plus size superconductor that breaks time reversal symmetry. And this type of superconductivity was theoretically predicted in this type of compound as a function of doping. And this was fairly old prediction, I think first like 2010. And then, so it was considered as a function of like doping, as a function of the ratio of these two of x of doping. So you at some point have either like you can have like two gaps, you can have three gaps, you have either pi phase difference that system breaks only one symmetry, or you can actually have a frustration and then to have twofold degenerate locking between these phases. And then we considered this problem, and then we have shown that this S plus I superconductor, they also could have this composite order, can have basically four electron condensate, but which one that breaks a discrete symmetry, discrete the two time reversal symmetries. This is where these two works, and essentially, which means instead of two components at the beginning of the talk, one has three components. three phases coupled by the same vector potential, but then this additional ingredient is interband Josephson coupling. So it also works in a similar way if you have just two-component system and then bilinear Josephson coupling, for example, in P plus IP superconductor or S plus ID superconductor. There are similar type of it just works. We also considered that in 2014 paper, and that works in a similar way. And then let me just show the simulation, the Monte Carlo study of the phase diagram of this model as a function of basically Q is inverse gauge field coupling constant. So essentially, it parameterizes magnetic field penetration length, and then one finds like three phases. This corner corresponds to high temperature. So at high temperature, small beta, system is completely disordered. Like of course there is like Elizur theorem. I'm talking a little bit when I write here averages. Just they're like a little bit loosely defined, but I will say there is hero system doesn't break any symmetry. Like if one would try to be more careful with terminology, so with high temperature phase, no symmetry is broken. Here, at weak gauge field coupling, system breaks. It is a superconductor which breaks one local symmetry, but it also breaks time reversal symmetry. This is a standard transition from superconductor which breaks time reversal symmetry to normal state. That occurs at weak gauge field coupling. But what was most interesting for us is that for that system, a significantly high gauge field coupling, they have a new phase, which is not superconducting. So basically, if one thinks in terms of the gaps, so one has phase disordered gaps. So it's like one should be careful on talking about disorder and gap fields. It's because it's local gauge theory. So like it's not like if I'm careful with formulation of say a system is non-superconducting, is phase disordered, the phases of the gaps are disordered, or complex fields equivalently, but there is order in the relative uh, phases of the gap. And since gap is a field which is constructed of fermion pairs, the product of the gap is a field which is constructed of four fermions. It's a four fermion condensate, but it is a four fermion condensate that breaks only discrete symmetry. In that case, it is just time reversal symmetry. In other words, at significantly strong gauge coupling, one can have a phase transition where one goes from low to high temperature. First, one loses superconductivity, but the system still breaks time reversal symmetry associated with the phase difference between the gaps. And like most advanced numerical computations showing that phase transition were done recently by Ilaria Makari, so she could give like a lot of details on this type of phase transitions. Now they're kind of very well established in the classical models. So yeah, so this is like conclusions of the theory part. So if one has a multi-component system, a particular multi-component gauge theory, as long as you have multi-component gauge theories, you have several Cooper pair instabilities of charged fermions, like electrons or electrons and protons, then the cheapest topological excitations are, have, are infinitely more expensive. They have either logarithmically, or if you have Josephson terms in your models, they have linearly divergent energy as a function of system size. But various bound states of them, they have finite energy per unit length, so finite energy in two dimensions, and correspondingly, instead of this Kostelis Tauris or Onsager-Feynman type of picture, one gets a picture where bound states of topological defects, composite complicated topological defects, can proliferate or can get vortex anti-vortex pair proliferation before individual proliferates. In terms of symmetries, it means that if you proliferate first composite topological defects without proliferating individual ones, you basically partially measure the order, you still retain non-trivial higher order correlations with systems. And this type of correlations, they could be either, let's say, this metallic superfluid, or charge for a superconductor, which is another parameter composed out of four fermions, or a contour fluid where only relative motion of pairs of fermions is dissipationless. So now, how much time do I have left?
I would say 5 minutes or so.
Okay, then I will try, to be very brief. There are like many interesting things about what is the uh, effective model of this type of counterflow condensate, and I will go to experiments. So, and 2001, this state was observed in experiment on BKFA by the lead experimentalist, first author is Vadim Grinenko. So essentially, the state was observed in time reversal symmetry was observed in a certain breaking of time reversal symmetry at a certain doping in BKFA. And this material was observed above superconducting phase transition, and that all signals the for fermion order parameter, like later NMR have shown that there is no spin magnetism and even no proximity to spin magnetism. There is no other mechanisms for the breaking of time reversal, trivial magnetic mechanisms for time reversal symmetry breaking are excluded. Then there are like a number of other anomalies in the state, such as Nernst effects, which there are like many subtleties about Nernst effects there, but it's definitely anomalous. Definitely, it is unusual. Then there is unusual ultrasound and unusual transport properties of various kinds. And then, so this is, maybe I will show, just flash a little bit. So, so basically muons detected spontaneous magnetic fields above magnetically and this is spontaneous Nernst effect, but it's like discussion, and essentially like specific heat is very remarkable here. So there is dead zero diamagnetic susceptibility, but specific heat jump fully develops. And this is like this is a reference samples at other doping. So the usual picture of a washout phase transition where specific heat correlates with onset of diamagnetism. And here, this is basically, since this is a time reversal, symmetry breaking, electron quadrupling condensates, order only in relative degrees of freedom. It has no Meissner effect, no diamagnetism. And so so let me, so okay, this like various other type of ultrasound. So some samples, this is like example of another sample. There is actually two specific heat features, and that the first specific heat feature, time reversal symmetry is broken, but there is absolutely no diamagnetism and no superconductivity, and it develops only at lower temperatures. So most of these critical temperatures are also suppressed by external magnetic field. And then, so what I started at the beginning, like all the arguments, it relied on the fact that magnetic flux quantum should be fractionalized to all of this mechanism to work, and moreover, there should be fractional magnetic flux vortices, and they should be much more expensive than integer vortex. And uh, in there are many studies of vortices in superconductors, and fractional vortices were never seen. And actually, we sent our samples to Cam Möller group, the leading group on scanning squid microscopy. And then indeed, like Yusuke, they found that uh, there are vortices. This samples, one can create vortices, like they develop a protocol, and they could create vortices on vortices, anti-vortices on demand that could carry basically a fraction of the flux quantum ranging from approximately 1/3 to approximately 10%. It is also the seen fractional vortices. So let me show you like this example. So this is uh, like you can see, there is like there are two vortices, and they have order of magnitude different flux, and they are created at the same position vortices carrying about 10% of the flux quantum. This is just superimposing these two pictures, showing that these are really true vortices carrying arbitrary fraction of the magnetic flux quantum, which are mobile objects, which are not, it's not like area dependent, this type of things. And that is like objects which are required in this type of mechanism. And since then, there were more important results showing this. Just 1 second. Showing this. So then, like very important paper by Yuhua Wang, they have shown like whole genesis. Not only they saw fractional vortices, but they have shown whole genesis how vortex is like two rows at two different measurements, two different kinds of squid measurements. But he observed how like integer vortex actually splits now in two parts. So basically, and each carrying a fraction of the flux quantum, and they each the flux quantum, and then and he also was able to observe it to all the way to very very low temperature. And finally, like this was together, like along with the quantization of the magnetic flux, like equally important concept is a core of a quantum vortex. And so, like in the stand, like is concept by Onsager, he first talked about concept of the vortex core in helium-4, and Feynman elaborated on it. And typically, there's one singularity, like a standard picture. There's one singularity, one core per quantum, per vortex quantum. And in this picture, which I outline, actually, magnetic flux fractionalizations and fractionalization implies there are like there should be two or three singularities associated with the fractions of the magnetic flux quantum, and this in the Honding's group, and this is the Kwansin, his postdoc, who did spectacular experimental work and with STM, and they have seen how the flux, how the vortex core singularity fractionalizes. So, therefore, basically, the like confirming the concept of fractionalization of the quantum vortices. And so, yes, and then so what how I would conclude is that so there are now experimental reports, many properties like were measured and are measured, and there's recently very important angular RPS measurement for this compound from Stanford, and so the raw reports of for electron condensate. This is a partial counterpart of metallic superfluid, which we discussed in the context of metallic hydrogen. The big difference is that it is not a superfluid; it breaks only discrete time errors of symmetry, but it is like it has properties which are principally different from both superconducting and normal states, such as spontaneous magnetic fields and unusual transport thermoelectric properties, unusual ultrasound behavior, and like the key thing, maybe which it would kind of require 1 hour more talk to elaborate, but I can mention it briefly. So one has this time erosion symmetry breaking electron quadrupling condensate. One has dissipationless local currents around impurities that create spontaneous magnetic fields, which, for example, are seen by muons, but DC currents are dissipative. So there is a peculiar subset of dissipationless flows allowed by the system, but not DC superflows for this particular aspect of that like what is the effective model of the state, and what I like about about this particular state is that the effective model for that is different from Ginzburg-Landau or Gross-Petaevsky model. So there are not so many effective models in condensed magnetism. There is Ginzburg-Landau, there is Gross-Petaevsky, and basically charged or neutral systems. There are various versions for that, but that model is actually more similar to a Skirmy type of model, the model that describes like this persistent currents that gives that muons see. And finally, so what is beyond the scope of this talk, like initially I mentioned that the BCS theory doesn't even allow to form this for electron order parameter and plug it into standard Hamiltonian, and for a long time there was no fully microscopic approach. So basically what I presented was one started with some low temperature effective field theory and then considered effective model, corrected it by fluctuations, and that way we demonstrated in existence of for fermion for electron condensate under certain conditions. But now also like there was a very recent paper where where like this Albert Samolenko on this picture. Where this paper it was demonstrated how to obtain for electron condensate directly in the microscopic theory. So I think, yeah, I can, yeah, maybe I can conclude. Yeah, can conclude at this stage, at this slide.
Thank you, Igor. Thank you very much. It's a real tour de force and a lot of rich physics, and I especially like the connection to the new experiments that you reviewed. So the talk is now open for any questions or comments. Maybe to start off with, connecting the first part and the last part. Of course, if we were to make these new phases of hydrogen, it would require high pressure cells, and we'd have to be doing measurements in situ, which makes the imaging much more complicated than these elegant new experiments that are being done, for example, those at Stanford with STM type techniques. So I'm wondering, can you say something about the scaling of the vortex cores, the sizes? What would be required to image that? Thinking about doing that through a diamond anvil, for example. How does it scale with magnetic field and so on?
Right. So with like if one would okay, like the contour, just to I will try to make to draw on a whiteboard. So what would be the um, so let me have a whiteboard, right? So the let's say what would be the metallic hydrogen type is for fermion condensate is where the only type of dissipationless motion would involve co-flow of electronic and protonic Cooper pairs. So in total for fermions. So that mechanism in principle supports this type of transition. And then in that state, so in principle, if one implants like pickup coil in diamond anvil cell, or potentially if one potentially that could be picked up like if one puts NV centers magnetometry setup uh, in in diamond anvil. I think there was like recently some works from Harvard, Norman Yao, if I recall correctly, um, putting NV centers magnetometry in diamond anvil cells. And perhaps one will, it might be like extremely difficult uh, to pick up this fractionalization of the magnetic flux quantum in diamond anvil cell because of uh, large difference between of masses between electrons and protons. That would imply very different ratio of fractions of the magnetic flux quantum. So uh, so now having a bit of experience with working with experimentalists who detect electronic counterparts of the states. Yeah, I want it might be difficult. Yeah, I want to be like a little bit conservative how easy it would be, like if it is within reach of magnetometry techniques for.
Mhm.
Like, was there any progress in one or another way to try to find vortices, like with, for example, NV centers in diving alveolar cells? Was it eventually
To my
any?
knowledge, no one has done that yet, at least not reported it. So backing off and not looking at metallic hydrogen, but looking at these other superconductors under pressure, the question
Yeah,
is,
yeah, exactly.
what would be required to image, these vortices as has been done at ambient pressure? So a good place to start would be with other superconductors, obviously.
Right. Yes. So yeah, I think it is like it's a little bit uh maybe like I heard that people wanted to use ultrasound probes in diamond anvil cells. So actually, some of our
Mhm.
co-authors on probing the states of matter by ultrasound, they actually, I think, they were working on trying to apply somehow these techniques. I don't know how realistic it is. So maybe actually that could be a route.
Yeah, that's a very good idea.
Just if
Right.
they
Hmm.
just to try to probe it in ultrasound.
Yeah, thanks.
Mhm.
More questions, comments?
I have a maybe kind of naive question, if that's okay.
Hmm.
Mhm. Yeah. Mhm.
Um, but if you are trying to just measure, I mean, if you're trying to look at these fractionalized vortices, I mean, would
Mhm.
there be a possibility of kind of teasing that out of a like a Hall measurement or something if you have these mobile vortices, just in a very intense field? It would be transport, it wouldn't be imaging, but
Right, to try to pick up fractionalization in was in whole, right?
yeah, yeah, that was what I said.
Uh, just I got a little distracted. Yeah, to so or maybe just sorry, I got maybe I started to think about something, got distracted. Could you please repeat the
Um,
question? Yeah.
yeah, because I was wondering if it uh because like if you're measuring maybe some kind of like Hall effect or you're measuring this vortex transport in like
Yeah.
a Hall
Mhm.
configuration under a huge magnetic field or something.
Yeah.
Um, because I mean in theory you should be able to measure if they're quantized. I'm wondering, are you aware if that's been done or attempted?
Right. So, like in like at least in the samples that in this material, this electronic material that we have, uh, there is like breaking of time reversal above superconducting phase transition, primarily seen by muons, but it also there is also unusual spontaneous Hall effect in zero uh, magnetic field. So we still have to understand it. I could only say that it is unusual, but I want to be conservative, so it's not yet published, and we're still kind of thinking about it because of with uh, uh, with the Hall effect. When one talks about spontaneous Hall effect, there is always like purely geometric contributions.
Yeah, yeah, of
So, but
course.
yeah, but there are so basically, but the geometric contributions they happen simultaneously when the transition is broadened, and
Yeah.
there the spontaneous the difference is that there's strong spontaneous Hall effect mm, away from broadened resistive phase transition.
Okay.
And but it's still, I would not draw any conclusions from this so far. Like I would say that we are trying to understand it, but it is yeah, in principle, yes, these probes they should be sensitive to all these transitions. How like yeah, like how easy yeah, but yeah, these experiments are being done, but we still need to understand a lot
Okay. Okay,
about
thank
them.
you.
Yeah, thanks.
Mhm. And also there's one thing, like if one looks at this type of flow fermion counterflow condensate or metallic superfluid, this when one talks about this condensate, which is like where order is only in delta 1, delta 2 star, or like C1, C1, C2, C2, C2 dagger, C2 dagger. So this condensate has no diamagnetism, and there are no vortex lattices formed in response to external field. So that is, but yeah, but in principle, there is still under certain conditions possibility for zero field spontaneous Hall effect in if it is a state is breaking time Dirac symmetry.
Okay, thank you.
Okay, thanks. Any more questions? Okay, if not, thank you, Igor, for a very enlightening talk, a wonderful review of your work, and we'll stay in touch. Thank
Yeah,
you all
thank
for
you just
joining us.
for invitation,
Okay.
and see you.
Yeah.
Hope
Good
to see you
evening.
at some point. Bye. Bye bye.